Now let's turn our attention to reactions that are not first order reactions. So there's two types of reactions that we're gonna consider in this course. The first one that we're going to talk about in this video is the second order reaction. At the end of this video, we'll talk about what if you have a zeroth order reaction. So let's consider the second order reaction first. Okay, so what we need to do is consider, right, to give the general expression for the rate law for a second order reaction with A being its only reactant. So if we're going to give the general reaction expression again, the rate would be equal to the negative change in the concentration of component A divided by the change in time. Okay, so that's what we talked about at the very beginning of this unit. If we're going to write a rate law, this would be equal to K, the rate constant, times the concentration of A. And because we know it's second order, that means that the exponent is going to be 2. So the concentration squared. All right. Now, the way that we did this, we got an integrated rate law equation for first order reactions. We had to use calculus to do this. Okay, and we're going to have to do the same thing again here. We apply the laws of calculus in order to derive this equation. Now, for this equation, we're gonna skip all that. So, without going into the derivation, what is the rate law equation what is the integrated rate law equation for second order reactions? It would look like this. The constant 1 over the concentration of substrate A at a certain point in time t is equal to the rate constant K times the time plus 1 divided by the initial concentration of component A. Now, this is a pretty important equation, so I'm going to go ahead and highlight this. But this is the reaction. This is the equation for a second order reaction. Now, if we're going to put this into a form like, to get a straight line like y equals mx plus b, the way this would work is that the 1 over a sub t, this would be your y, k would be your m, that would be your slope, t would be your x, and then 1 over a sub 0, that's going to be your b. So it's already pretty much in a form that's going to be like y equals mx plus b. And so if we plot the concentration of A versus T, we get a figure that looks something like this. Okay? Now, all right, and this is actually pretty much the same picture that I showed you previously when we talked about half-lives. Now, is this a straight line? Nope, sure isn't. Because look at that. That is an exponential decay curve. So how do we get a straight line out of this? Well, we can't graph the concentration of A versus T. We're going to have to graph the reciprocal, 1 over the concentration of A versus T. And that will give us a straight line. Okay, now at this point, we're ready to do an example question. And this, I'm going to be honest right off the bat. There's a lot of stuff to this question, but this is an outstanding question that ties a lot of the stuff that we talked about together. Let's check it out. So let's take a look at this problem. At elevated temperatures, nitrogen dioxide decomposes to nitric oxide and molecular oxygen. And you've got this equation, 2 moles of NO yields 2 moles of NO plus O2. Okay. And that should be, I apologize, there should be a 2. It's NO2, not NO. All right. The concentration time data for the consumption of NO2 at 300 degrees Celsius are as follows. And so we've got this table. So time 0, you've got a concentration of 8 times 10 to the minus third. Time at 50 seconds, concentration's dropping down to 6.58 times 10 to the minus third. So it looks like the concentration of NO2 decreases as the time increases. Makes sense. So this NO2 needs to be your reactant. All right. So here's what we're asking. Part A, what is the order of the reaction? Part B, what is the value of the rate constant for the decomposition of NO2? Part C, what is the concentration of NO2 at T equals 20 minutes? Part D, what is the half-life of the reaction when the initial concentration of NO2 is 6.00 times 10 to the minus third molar? And then Part E, what is the half-life when the initial concentration of NO2 is 3 times 10 to the minus third molar? All right, so we've got a lot of stuff going on. Okay, so the first question is this. What is the order of the reaction? Okay, one thing we could do that could give us this information very quickly is if you have access to a computer, you can actually create graphs that will help us ascertain what kind of reaction we've got. Okay, so if we should graph, we're going to make 3 plots. One plot, and I'm going to make a note, is going to be the concentration of NO2 versus time. Okay, a second plot that we're going to make to follow what we did for first order reaction should be the natural log of the concentration of NO2 versus time. And then the third one should be 1 over the concentration of NO2 versus time. All right, so what we're looking for in these 3 graphs is we're looking for a straight line. The one that gives us a straight line is the one that's going to tell us what order this reaction is. So one of these graphs, either the concentration of NO2 versus time, the natural log of NO2 versus time, or the 1 over the concentration of NO2 versus time, one of those 3 has to give us a straight line. Whichever one gives us a straight line, now we know what order it is. All right, so let me go ahead and give you that information. So what we're looking at before we take a look at the graphs, I just drew a line down this table. This is the original data, all in one shot, okay, in 2 columns instead of split off into 4. So what I did was take the concentration of NO2 and take the natural log of it, okay, and we got those numbers. I also went back to the original concentration of NO2 and took 1 over the concentration to get those numbers as well. So hopefully, if we get a straight line from the natural log of NO2, that tells us it's first order. If we get a straight line from the reciprocal, that's going to tell us that we've got second order. All right, so what we're looking at on the right-hand side, these are our graphs. So it looks like we've got a decay curve going on for the concentration of NO2 versus time. It looks almost straight-ish for the natural log of NO2 versus time, but we definitely have a straight line for 1 over NO2 versus time. So that's our winner. So based on the graphs, we can see that the graph, and let me get part A down. So based on the graph of 1 over the concentration of NO2 versus time, that gave us a straight line. And so that tells us that this is going to be second order. There it is. So that's our first part. All we had to do was graph the data and see how it comes out. And based on that, we know how it works. So there it is. There it is. All right, so now that we know it's a second order reaction, part B is asking this. What is the value of the rate constant for the decomposition of value of the rate constant for the decomposition of NO2? All right. Now, going back to our equation, if we take a look at this equation, the slope of this line should indicate the rate constant. So if we're able to calculate the slope of the line. And that's kind of what we're doing in this picture. So taking a look at this graph, if we pick out certain 2 points, okay, and I'm gonna highlight those points. If we are able to calculate the slope, that's going to be the k. So there it is. Let's try this out. So to do part B, the slope of the second order plot tells us k. And so if we calculate that, which is going to be the slope is going to be the change in y over the change in x, if we take a look at those 2 points, it looks like you've got 1 point that's going to be, that has a y value of 341, and the x value is going to be 400. For the other point, it's going to be, the y value is 152, and the x value is 50. And I'm just getting those from the graphs, from those 2 points. All right. Just to clarify, let me make those 2 points. Let's write those out. So one point that we used was 400, 341, and then the other point that we used was 50, 152. Okay, and so based on this, if we take 341 minus 152 divided by 400 minus 50, that gives us 0.54 mole to the molar and minus first, seconds to the minus first. And there it is. All right, so that's our part B. So that was nice. All right, now part C. Part C is asking us. Let me flip back to my notes. Here it is. Part C, what is the concentration of NO2 at T equals 20 minutes? Okay, what is the concentration of NO2 at 20 minutes? Well, first off, we got to know how many seconds, because all of this stuff, all the time is given in seconds. We know that we got 20 minutes. So the first thing we need to do is figure out how many seconds this is. So if we got 20 minutes, and then if we convert minutes to seconds, so 1 minute has 60 seconds in it, 20 times 60 gives us 1,200 seconds. Okay, so that's how we know. That's how much we've got. Now, 1,200 doesn't fall on our table. The highest it goes is 500 seconds. So we got to actually calculate what's the concentration. All right, so to do that, we're going to have to use the second order rate law. So that equation again is going to be 1 over the concentration of NO2 at a certain point in time t is equal to kT plus the initial concentration, 1 over the initial concentration of NO2. All right, now according to the data that we have up here, the initial concentration, and let me write that out, NO naught is going to be 8.00 times 10 to the minus third. All right, so that's how we know that's our concentration. So what we're going to do is basically pop in our stuff and solve for NO2 at 1,200 seconds. All right, so let's do that. So K is our rate constant that we just found in the last part, 0.54 molar to the minus first, seconds to the minus first. Okay. T, we know, is 1,200 seconds. Okay. And then 1, we're going to add plus 1 over the initial concentration, which is going to be 8.00 times 10 to the minus third molar. Okay. And then this is all equal to 1 over NO2. So we're going to have to do, we'll deal with the 1 over NO2 in a minute. All right. So if we take 0.54 times 1,200, 0.54 times 1,200, that should, and then we add 1 over, let me get my calculator out. I just put it away. All right, so 0.54 times 1,200, okay, that gives us 648. Okay, and then the seconds to the minus first cancel out with seconds, so we know that this is going to be molar to the minus first. Now we've got 1 over 8.00 times 10 to the minus third molar as well. All right, so let's do that. So I'm going to add that. 1, so 648 molar minus 4 is plus 1 over 8.00 times 10 to the minus third. And so that value that we get should be 773. Okay, now molar to the minus first, and we're good. We are good. All right, now this is going to be equal to 1 over concentration of NO2 at 1200 seconds. So let me write the 1200 in. So now we've got to do some finagling in order to get the concentration of NO2 by itself. If I multiply both sides by the concentration, okay, and then I'm going to get 1 is equal to 773 times the concentration of NO2. If I then divide both sides by 773, I would get this, that the concentration of NO2 at 1200 seconds is going to be equal to 1 over 773. And so that is going to be equal to 1.29 times 10 to the minus third molar. Now, there is a way to check. Does this value make sense that we just calculated? Well, going back to the table, we know that the time was off the chart, but the final concentration, the final concentration was 2.53 times 10 to the minus third. Is the value that we calculated lower than this value? Yeah, so it makes sense. This number does make sense that it's going to be that value. Okay, all right, so that's part C. Next question, part D. All right, so part D asks this. What is the half-life of the reaction when the initial concentration of NO2 is 6.00 times 10 to the minus third molar? Oh, so another thing that we could talk about is if we were, for the first order reaction, we derived a really useful equation to get the half-life. Can we do the same thing for this? Okay, and I'm going to skip just a little bit down in the notes so we can get to that. So let's derive the general equation for the half-life of a second order reaction. So this equation, let me write the second order equation again. So 1 over A at a certain point of time t is equal to kT plus 1 over the initial concentration of A. Okay. Now, if we're at half-life, half-time, the concentration of A is going to be at a certain point in time t is going to be equal to the initial concentration of A divided by 2, because by definition, once you complete one half-life, that's the amount of time it takes to break down the half of the original mass. Okay. All right, so what we're going to do is take this expression that we just put in, that we just got, and we're going to solve, we're going to put that into AT. Okay. And once we do that, and, clean up a lot of the mess here, we get, that the half-life, T1 half, is going to be equal to 1 over the rate constant K times the initial concentration of substrate A. Okay. Now, how is this equation different from the first order case? Keep in mind that the half-life is a function of the initial concentration of your reactant. And so that's how this is different. The last time, all we needed was the rate constant. Now you've got a concentration that you got to deal with. So now that we have that expression, we can actually use that to figure out the half-life. So again, the question that we're posing for part D here, question is this. What is the half-life of the reaction when the initial concentration of NO2 is 6.00 times 10 to the minus third? Okay, so let's do that. So half-life is equal to 1 over K times the concentration of NO2 initial. So this would be equal to 1 over, the K for this reaction is going to be 0.54 molar to the minus first, second to the minus first, times the initial concentration of NO2, which is 6.00 times 10 to the minus third, based on what we're told from this problem. So if we take 1 divided by the product of 0.54 times 6.00 times 10 to the minus third, that should give us a half-life of 309 seconds. Okay. Now, if we do the same thing for part E is asking us this time, what is the half-life when the initial concentration is 3.00 times 10 to the minus third? So let's try that. So we're going to do the same thing like we did in the last problem. K is still going to be 0.54 molar to the minus first, seconds to the minus first, times the concentration. This time the initial concentration is 3.00 times 10 to the minus third molar. All right. So when we do this one, 1 divided by the product of 0.54 times 3.00 times 10 to the minus third, that time is 617 seconds. And so that is a really nice problem for the second order reaction. All right, so we got another problem that we can try out. So let's do this. So another problem we can try is this one. A reaction that consists of 2 of the same units combining is called a dimerization reaction. One such example is this, where you have 2 moles of C4H6, and this isn't a gas, and this yields 1 molecule or 1 mole of C8H12, also gas. This reaction is second order in the reactant with the rate constant 6.14 times 10 to the minus 2 molar to the minus first, second to the minus first. Given that the initial concentration of this was 1 molar, how long does it take for this concentration to reach half molar? So we're looking for the half concentration. All right. So we could solve this 2 different ways. One way, since this is we're looking at the initial concentration is 1, and we're trying to figure out how long it takes to get to half, we could, since we're looking at, we could use just the half-life equation, or we could use the full-blown second order equation. Now, I'm going to go for that second option. Let's use the full-blown equation just so we can get some more practice at using that equation. So to write that equation out, 1 over the concentration of C4H6 at a certain point in time t is equal to KT plus 1 over the initial concentration of C4H6. Okay. Now, we know the initial concentration, we know the final concentration, we know K, we just don't know T. So we're going to pop in our values and see what we've got. So we've got 1 over, and we're looking at 0.5 molar is equal to K, which is 6.14 times 10 to the minus second, molar to the minus first, second to the minus first, times T, which is what we're looking for, plus 1 over the initial concentration, which is 1 molar. Okay, so 1 over 1, that's 1, so that's nice. And 1 over 0.5, that's nice too. All right, so if we take 1 over 0.5, that gives us 2. So right off the bat, we know on the left-hand side that's equal to 2. And that's equal to 6.14 times 10 to the minus 2 times T plus 1 over 1, which is 1. Okay, so if I subtract 1 from both sides, we get 1 equals 6.14 times 10 to the minus 2 times T. So to solve for T, if I divide both sides by 6.14 times 10 to the minus second, I should get that the time E minus second. The time should be, I'm getting about 16.3 seconds. So that's how long the concentration will take. That's how long it's going to take for the concentration to lose half of its strength. Now, if we were to calculate the second successive half-life, okay, so in this case, the initial concentration will be 0.5 molar. Second concentration, or the time that we're looking for, is going to be the concentration is going to be 0.25. So we've got 1 over 0.25 molar is equal to 6.14 times 10 to the minus 2 times T plus 1 over 0.5 molar. All right, so now if we take 1 over 0.25, that gives us 4, and that's equal to 6.14 times 10 to the minus second T plus 1 over 0.5, that's going to be 2. Okay, so we need to solve for T. If I subtract 2 from both sides, we get 2 equals 6.14 times 10 to the minus second T. So if I divide both sides by T at this point, or by 6.14 times 10 to the minus second, 2 divided by 6.14 times 10 to the minus second gives us 32.57. So I'm just going to round this up to 32.6 seconds. Okay, now to double check, if we go back to the first value that we calculated, the 16.3, if that's the first half-life, then the second one should be just double that. So 16 doubled should be 32. So the time half-life that we calculated for the second half-life is 32.6 seconds. So that makes sense. That makes sense of what's going on. Okay, so is this consistent with the equation that we derived in the image? Yes, it's absolutely consistent because it's got to be doubled. Okay, so now here's our question. Let's calculate the concentration of remaining product after 25 seconds. So we know now just by eyeballing it, the first half-life is 16.3 seconds. The second half-life is 32 seconds. So this time at 25 seconds falls right between the two. So right now we know that the concentration at this time has to be between 0.25 and 0.5 molar. All right, so let's try this out. So to solve this, we've got to use the full-blown equation, the full-blown second order equation. So 1 over the concentration of our species, 6,4H6, at a certain point in time t is equal to kT plus the initial concentration. Okay, well, so let's put in our values. We know that we've got 25 seconds, so we're going to solve for that C4H6, but this time I'm going to put in that time. Okay, at 25 seconds. That's equal to K, which we know, that's 6.14 times 10 to the minus second. Molar minus first, second to minus first. T, we know, is 25 seconds. Plus the initial concentration. So I'm going to use the initial concentration from the problem, 1 molar. All right. So let's try to clean this up a little bit. So 6.14 times E raised to the negative second times 25 seconds. So that stuff gives us 1.535. And if we add 1 over 1 plus 1 to that, so we're going to get 2.535. Now we have 1 over the concentration over here at 25 seconds. So we need to solve for the concentration. Okay. So if we multiply both sides by the concentration and then divide by 2.535, we get that the concentration, C4H6 at 25 seconds, should be equal to 1 over 2.535. And that concentration should be 1 divided by 2.535 gives us 0.394 molar. Now, does this number make sense based on what we've seen? Well, we know that the concentration had to be between 0.5 and 0.25, so this number being 0.9394, yes, that does make sense. That sounds very reasonable. Before we transition to another topic that is connected with kinetics, let's take a look at the zeroth order reaction. So, what is a molecular level situation where something like this could occur? Remember that when we talked about this way back when, that for a zeroth order reaction, the rate is not affected by the concentration. So the rate of the reaction is not affected by the concentration. So the concentration could be doubled, tripled, quadrupled, or halved or quartered, and it's still not going to have any reflection on what the rate does. So how would we determine whether or not a reaction is zero order? So let's start from where we know. Let's start from the point of view that we know. If we write a general expression for the rate, we know that the rate is equal to the negative change in the concentration of our substrate A divided by the change in time. Okay? And if we were to write a rate law for this reaction, the rate law would be K times the concentration of A, but the concentration of A would be raised to the zeroth power. Now, anything raised to 0 automatically is 1, so that means that the rate would be equal to the rate constant. Okay, so there it is. The rate would be equal to the rate constant if we were to graph this. Now, what would a zero order reaction look like if we're going to show this as a picture? So let's say you got a reaction going on, and here's a picture. You've got molecules of NH3, okay? And on the surface of this metal, we're trying to get those NH3 molecules to basically place themselves inside the nooks of the metal atoms. So every time there's a nook, that's where we want to place a metal atom. Now, because the NH3 molecules are somewhat bulky, okay, and as the molecules on the surface decompose, they are replaced by molecules from the gas phase so that the number of NH3 molecules on the surface remain constant. So as they decompose to give you H2 and N2, those two will also be in competition for that space on the metal. Now, so what this is really telling, if we were to sum up what we're seeing in the picture, what this is saying is that the rate is determined by the number of locations available for NH3 to react on the surface. So if you double or you triple the amount of NH3, that's all well and good, but what's really holding things up are the numbers of these crevices on the surface of a metal. If there's only 5 spots and you've got 10 molecules, then everything's going to be held up because you're held up by the number of places that you can dock those molecules. So that's kind of what a zeroth order reaction is. It doesn't matter what the concentration of NH3 is. It could be double, tripled, or whatever. What's holding everything up is going to be the number of molecules. All right, and finally, to summarize everything that we're looking at, this table is, and this is a really, really, really nice table. Actually, to be honest, on the exams, I do give this table to students. This pretty much summarizes what the rate law, the integrated rate law, the graph, how do you determine K, and the half-life. How do you determine that information for the zeroth order, first order, and a second order reaction? All right, so now based on this information, And based on everything that we talked about so far in this chapter, you should be able to write a rate law. You should be able to figure out if it's a first, a second, or a zeroth order reaction graphically, and then also be able to analyze a chemical reaction or a chemical situation using the integrated rate law.